This video offers a brief guide to Heapsort and Binary Heaps, covering what they are and how they are implemented. Heapsort is an in-place sorting algorithm that makes use of a binary heap data structure to make the sorting efficient. The algorithm was introduced by Jonathan Williams in 1964 and adapted to perform in-place sorting by Robert Floyd, also in 1964. One property of Heapsort is that it is not a stable sorting algorithm, in the sense that sorting does not preserve the input order of identical keys. In terms of complexity when sorting n data items, the average case performance of Heapsort is big O of n log n, matching the popular quicksort algorithm. However, it has the advantage that its worst case complexity is also big O of n log n, which is better than quicksort. While we require linear storage for the original container of items to be sorted, the storage overhead of the Heapsort procedure itself is constant, thanks to its in-place implementation. Some example applications of Heapsort include its usage in the Linux kernel, where comments helpfully scattered through the open source code explain that Heapsort is preferred to quicksort, despite the latter being typically slightly faster, because Heapsort avoids the worst-case quadratic sorting cost of quicksort on adversarial inputs. Heapsort is also used in introsort, which is a hybrid algorithm that starts with quicksort, but switches to heapsort or insertion sort, depending on the characteristics of the data being sorted, in order to avoid the worst-case behavior of quicksort and benefit from the speed of insertion sort in small regimes. To implement Heapsort, we first look at an important data structure called the binary heap that comes in two main flavors. A max-heap is a binary tree that satisfies two properties. First, the shape property, which states that the binary tree is complete, in the sense that all levels except the last are full, and if the last is not full, then it is filled from left to right. It also satisfies the max-heap property. The key of each node in the tree is greater than or equal to the keys of its children. To make this more concrete, here is an example max-heap. It is a complete binary tree, and it satisfies the max-heap property, since for any node, let's take the root for example, its children are less than or equal to it. This, on the other hand, is not a max-heap. Although it does satisfy the max-heap property, it is not a complete binary tree, since the last level is not full from left to right. The node here is missing. A min-heap is similar to a max-heap. It satisfies the same shape property, but rather than the max-heap property, it has a min-heap property, which is that the key of each node is less than or equal to the keys of its children. Here is an example min-heap. Again, we see that it is a complete binary tree, with all levels full except the last, which is filled from the left. We also see that it satisfies the min-heap property for any node on the tree, say this one with key 3. Its children both have keys that are larger than or equal to 3. A last point here. We often drop the binary part of binary heap, since all heaps we will concern ourselves with here use binary trees. However, so-called D-array trees with D greater than 2 children are also possible. We can represent a heap whose size is heap size using an array A of length n, provided that n is greater than or equal to the number of nodes in the heap. For this description, we'll focus on the max-heap, which is the heap variant used in Heapsort, but the min-heap variant is essentially symmetric. In the array representation, parent-child relationships are represented implicitly with indices. For this, the root node of the heap is stored at array index 0. Then, given a node with index I, the parent node is stored at the index given by the floor of I-1 over 2. The left child is stored at index 2i plus 1, and the right child is stored at index 2i plus 2. Given this scheme, we can restate the max-heap property as saying that A of I is less than or equal to A of the parent of I for I ranging between 1 and the number of nodes in the heap. To make this a little clearer, let's return to the max-heap we saw earlier in binary tree representation. To convert this to array representation, the root node is stored at index 0, while its left child goes to 2 times 0 plus 1, which is 1, and its right child goes to 2 times 0 plus 2, which is 2. Then the children of the node stored at index 1 are stored at index 3 and index 4, and the left child of the node at index 2 is stored at index 5. One alternative way to visualize this array is as a kind of hybrid that shows the correspondence between the tree and the array more clearly. Next, we look at the height h of a binary heap, which can be related to the number of keys n through the expression h equals the ceiling of log of n plus 1, i.e. h is big theta of log n. To prove this claim, we first observe that thanks to the shape property, the heap is a complete binary tree. That means that a heap of height h has at least 1 plus 2 plus 4 plus ... plus 2 to the h minus 2 plus 1, which is equal to 2 to the h minus 1 minus 1 plus 1, or 2 to the h minus 1 nodes. This extreme case occurs when there is only one node in the lowest level of the tree. We can also see that a heap of height h has at most 2 to the h minus 1 nodes, which occurs when the lowest level of the tree is completely full. From these two extremes, we have that n lies between 2 to the h minus 1 and 2 to the h minus 1. Taking logs gives us that h is less than or equal to log of n plus 1 and greater than or equal to log of n plus 1. Together, this implies that h is equal to the ceiling of log of n plus 1, completing the proof. In order to maintain the max-heap property as operations are performed on a heap, we fix violations that arise by bubbling keys that violate the property down the heap until they are once again less than or equal to their parents. This is achieved with a max-heapify helper function that takes in the index I that corresponds to a possible violation. This helper function assumes that the left and right children of index I are themselves valid max-heaps. The max-heapify function takes three arguments: a, the array underlying the heap size, and the index I of a node that may violate the heap property. We proceed by computing the left child and right child of I. We also introduce a max-I variable that will keep track of whether node I or one of its children has a larger key, and we initialize this variable to I. If I's left child's key is larger, we update max-I to point to the left child's index. If the right child's key is larger than either the key of node I or its left child, we point max-I to its index. If max-I no longer points to I, then we swap the elements at I and max-I. Finally, we recursively call max-heapify, using max-I as the index to focus on. Our code here uses two further helper functions: leftChild, which computes the index of the left child as 2 times I plus 1, and rightChild, which computes the index of the right child as 2 times I plus 2. To give a sense of how this works, let's look at an example heap with a violation at the root. We duplicate for clarity and assume that we call the function with a, heap size equals 6, and I equals 0. We compute the index of the left child and right child and set max-I to point to index I, which here corresponds to the root. We compare the left child's key with that of the root and find that it is larger, so we update max-I. Then we compare this with the key of the right child, which is larger still, so we update max-I again. Since max-I no longer equals I, we switch the elements and call max-heapify again, this time with I at the previous value of max-I. We compute the left and right child and initialize max-I to I. We check if the left child has a larger key and find that it does, so we update max-I. There is no right child of I, so we skip. Since max-I does not match I, we swap the elements and call max-heapify again, with I as max-I. We compute the left and right child and set max-I to I. The first if statement evaluates to false, and so does the second. This time, max-I equals I, and we are done. Our max-heap is now valid. The complexity of this operation is big O of h, or equivalently, big O of log n, where h is the heap height, since we only move downwards along a single path through the heap. We now come to the process of building a max-heap. Somewhat remarkably, this can be done from an unsorted array in linear time. To do this, our first observation is that each leaf node is automatically a valid max-heap of size 1. So our strategy is going to be to call max-heapify on each element in the left half of the array. Our build max-heap function takes in an array A. It computes the heap size as the length of the array. Then we use a for loop to iterate from the element on the left of the middle of the array down to the 0th index. iterating over the internal nodes and calling max-heapify as we go. Let's see this in action on an example array with the corresponding binary tree visualized to the right. We start by duplicating for clarity. Calling our function with this array, we first compute the heap size, which here is 6. Then we start to iterate, starting from a value of I equals 2, and we call max-heapify. Since 5 is bigger than 4, the only child of this node, nothing happens. So we move to I equals 1 and call max-heapify, which swaps 6 and 2. Finally, I moves into position 0, and we call max-heapify, which swaps 0 and 6, then swaps 3 and 0. And we are done. We've built a max heap. We now show that max heap construction has linear complexity. First, we note that our build max heap function contains a for loop that runs from the floor of n over 2 minus 1 down to 0. So we know that the cost of heap construction is bounded below. It's big omega of n. In order to show that construction is big O of n, we can write the total cost as being a summation of the various possible node heights in the heap, where at each height we count the number of nodes and the cost of calling max-heapify at each node. To make further progress, we use 3 observations. First, a heap with n keys has a height that is the floor of log n. Second, a heap with n keys has at most the ceiling of n over 2 to the h plus 1 nodes at height h. Third, as we've seen, the cost of max-heapify is big O of h for a node at height h. Combining these tells us that the cost of building the max heap is the following, where we've applied our first observation about the number of node heights to produce the limits of summation. We've applied our second observation about the number of nodes at height h to produce this term. And we've applied our third observation about the cost of max-heapify to write the cost as an arbitrary constant c times h. Now, this is less than or equal to the following, where we get the less than or equal to by noting that the ceiling of n over 2 to the h plus 1 is less than or equal to n over 2 to the h. This follows from the general rule that the ceiling of a variable u is less than or equal to 2u whenever u is greater than a half, which is the case for our expression involving n and h wrapped in the ceil operator. Next, we can move c and n outside the summation. We can also bound this with a summation that runs up to infinity, since all terms are positive. Now we have a convergent series that sums to a constant. We can rewrite this as our constant c times n times some other constant, which finally gets us to big O of n, as required. We now have the building blocks we require to implement heap sort. We'll first describe a naive heap sort function that can be called on an unsorted array A. This function will hopefully make the rationale for our final heap sort a little clearer. We call build max-heap to convert the array into a heap and calculate the initial heap size as the length of the array. We then create a list to store the result of the sorting operation. Then we begin a while loop that iterates while the heap size has more than one element. This picks the maximum from our heap and places it in the last position of the sorted output, swaps the maximum with the last element in the array, decreases the heap size by 1, and calls max-heapify on the 0th element, since it may now violate the heap property. When this loop is completed, we have a heap size of 1, and we copy the last element over and return the result. While there is nothing wrong with this approach, it uses extra memory to store the output in an additional array with the same size as the input array, which is not strictly necessary. For this reason, heap sort is most commonly implemented with a clever trick proposed by Robert Floyd to perform the sorting in place. As before, we call build max-heap and compute the initial heap size. However, rather than allocating a further list to store the outputs, we go straight into the while loop. Here we swap the 0th and last element of the heap, decrement the heap size, and call max-heapify on the 0th index. That's it, the whole function. It may not be immediately intuitive why this works, so we'll walk through an example unsorted array, which we duplicate for clarity. After calling heapsort on A, we first call our build max-heap helper function to convert the array into a max-heap. We compute the heap size, which here is 4, corresponding to the full array. Then we reach our while loop and step inside to swap the 0th and last elements, which we can see puts 5 where we want it to go. We reduce the heap size by 1 and call max-heapify on the root, which moves up key 4. Our heap size is still bigger than 1, so we again swap the 0th and last element, putting 4 into the right place. We decrement the heap size and call max-heapify on the root, which moves up key 3. Then it's back into the while loop, with another swap of the 0th and last element, which gets 3 into the right place. We decrement the heap size and call max-heapify, which will do nothing. Our while condition now evaluates to false, so we are done. And as if by magic, our array is now sorted. The complexity of this operation is big O of n log n, since we do n-1 iterations of the while loop, and each call to max-heapify is big O of log n. In addition to their use in Heapsort, binary heaps are also often used to provide an efficient implementation of priority queues. A priority queue is an abstract data type that contains a collection of values, each of which is associated with a particular key. Just as we saw with heaps, there are max priority queues and min priority queues. The max priority queue interface supports operations like getMax, which returns the value with the largest key, and popmax, which removes the value with the largest key from the priority queue and returns it. Then we have insert, which inserts a value with a given key, and increase key, which increases the key associated with a given value. For completeness, the interface for min priority queues also supports insert, but combines this with getMin, popmin, and decrease key. There are many applications of priority queues. A few examples include bandwidth managers, typically with a max priority queue to ensure that the highest priority packets are sent. Job schedulers, also typically with a max priority queue to ensure that the most urgent job is scheduled next. Dijkstra's shortest path algorithm, usually with a min priority queue, and Huffman coding for compression, also typically with a min priority queue. When providing an implementation of the max priority queue interface, we'll assume that keys and values are stored as Python dicts with key and value fields. We also assume that we have defined a class called maxpq, whose attributes are heap size and an array underpinning a heap. The getMax function simply returns the value associated with the 0th element in the heap backing the priority queue. As such, it has constant time complexity. The popmax function begins by finding the max value. Then we swap the 0th and last items in the underlying heap, decrement the heap size by 1, and call max-heapify at index 0 to restore the heap property before returning the result. Thanks to the call to max-heapify, this has complexity big O of log n. Let's see this in action on an example priority queue with numbers as keys and letters as associated values. We'll duplicate for clarity. After calling popmax, we first obtain the value associated with the maximum key via the getMax function, which here is the letter B. We then use the trick we saw earlier of swapping the 0th and last elements in the heap, reducing the heap size by 1 and calling max-heapify on the root to restore the heap property. Finally, we return the max value B. We next look at the increase key function, which takes in an instance of a max priority queue, a key, and a value. The function first initializes a counter, I, and iterates over the values in the priority queue to find the index of the heap where the target value is stored. Next, it verifies that the provided key won't decrease the current key associated with the value. Provided this check passes, the key is updated. Since this may have introduced a heap property violation, we then bubble the node up the heap with a while loop that checks if a node's key is greater than its parent. If it is, the two are swapped. Then I is updated to its parent. We'll see this in action on the same max priority queue as before. Again, duplicating for clarity. We'll assume that we call increase key with a key of 7 and a value of L. We initialize our counter I to 0 and iterate over the values until we find L, which occurs at I equals 3. At this point, we check that 7 is greater than or equal to the current key of 2, which it is. So we update the key associated with L to 7. Since this has introduced a heap property violation, when we reach the while loop, it evaluates to true, and we swap the ith entry of the array with its parent, then update I to its parent. We check the condition again, find that I's key is still greater than its parent, swap again, and move I up to the parent. We are now at I equals 0, so the while loop exits, and we are done. Our heap is once again valid. As with popmax, the complexity of increase key is big O of log n, which comes from the while loop moving up the height of the tree, which is proportional to log n. Finally, we come to the insert function, which takes as arguments an instance of maxpq, a key, and a value. If the heap size matches the underlying array, then we expand the underlying array to avoid a heap overflow. We then provide a temporary key that we assign to -infinity to prevent heap violations and ensure that we are below the provided key, and use this to add the value to the array. Then we increment the heap size and call our increaseKey helper function to attach to the value the key we originally specified. We'll look at this operating on an example max priority queue, which we duplicate for clarity. We'll call our function with a key of 8 and a value of g. First, we check if the heap size matches the array size. It does, so we expand the array by 1. Next, we assign a value of -infinity to tempKey and place it together with the value g into the array. We increase the heap size so that it includes this new pairing, and finally call our increaseKey helper function, which increases the key to 8 and bubbles it up the heap. Thanks to our use of increaseKey, the overall complexity of insert is big O of log n. To summarize, we've seen that the important max priority queue operations of popping the max element and inserting a new element can both be done in big O of log n time. With a few modifications, we can similarly implement the important min priority queue operations of popping the min element and inserting new elements in big O of log n. The low complexity of these operations makes heaps an attractive choice for priority queue implementation. In the video description, you can find links to Python code to implement heapsort, binary heaps, and priority queues, slides, and references. I hope you have a wonderful day.